Today we're going to look at some definitions. We're also going to start the ideas that are going to get us into derivatives and slopes of tangents. But first of all, what is a couple of our important definitions? First one is a secant line. Now that's a line that cuts through a curve. So if I have a parabola here and I drew a line like this, that would be a secant line. It cuts through the curve. Usually at 2 points, but it could cut through at more than 2 points. You could have a secant line cut through at 1 point if it just went right straight through it. But for our purposes, we're going to be talking about secant lines that go through 2 points. A tangent line, and you've done tangents in grade 9 when you did a tangent to a circle, but tangent lines don't exist only to circles. Tangent lines can be on any curve, and it's a line that touches a curve at 1 point, and it usually doesn't cut through the curve at that point. So for example, if I had a parabola, this would be a tangent line touching it at 1 point, and it doesn't cut through the curve. There's 1 point on the parabola. Well, there's more than 1 point, but at the vertex of our parabola, this would be the tangent line. You wouldn't draw the vertical line cutting through it. There is an example, or there's a couple of examples where you could have a tangent line that actually cuts through the curve. One of those examples is with an x-cubed graph. If I have an x-cubed graph, the tangent line at 0 is actually flat, and it cuts through the curve. So an x-cubed graph, when you think about multiplicity and you think about us drawing graphs with bends, those bends actually flatten out completely at that point. And when you draw a tangent at that point, it's completely flat and does cut through it. But for the most part, a tangent line is, like we see on this parabola, a line that touches it but doesn't go through it. Now, when we talk about rates of change, there's two rates of change that we're going to be looking at. One is an average rate of change, okay? And the other one is an instantaneous rate of change, which we'll have in a second. You can write it down. Average rate of change, instantaneous rate of change. So for example, if we talk about speed, because speed is a rate of change. Speed tells you how many kilometers you've gone in an hour. So if I was traveling from here to Portage la Prairie, which is 85 kilometers away, let's say. I'm not sure exactly how far Portage la Prairie is. It's probably pretty close to that. And it took me an hour. I would say that my average rate of change was 85 kilometers per hour. That was the speed on average that I traveled from Portage la Prairie. Now, that's not actually what happened. I got in my car, I hit a stop sign, and then I hit a red light, and then finally I got to the highway, and once I got to the highway, I sped up. The speed limit was 100, so I went 100, but at times I was going 105, and then I realized I was going too fast, and I brought it back to 102, and then I thought 105 is really not that bad, so I went 110 the rest of the way. And every time that I looked down at my speedometer and I saw it at that instant, that is my instantaneous rate of change. That's how fast I was going at that moment. But if I look at the whole thing is my average rate of change. Now, rates of change are really slopes. It's a change in one over a change in another thing. So when we think about speed, it's a change of distance and a change in time. And that's what makes up a slope. Here are some different notations. You might remember the slope of a line, rise over run, y2 minus y1 over x2 minus x1 from back in grade 10 when you studied lines. Another word for slope is gradient. In physics, do you use this delta symbol for change? Change in y over change in x? And what we're leading towards is the derivative. The derivative is another measure of rates of change of slopes. So let's make up.
So slope and gradient are for all intents and purposes are the exact.
Yeah, they're like synonyms.
They're synonyms. All right.
Yeah. So, I mean, you'll hear those words in different places. They talk about slopes of mountains. They talk about a gradient of a road, how steep that road is. You could say slope of the road, but they generally do use the word gradient more for that. So they're interchangeable words, and we'll use them in both places. So let's consider the following graph here. We're going to make up some values. We're going to put time down here and distance here. Okay? Distance from something. Let's say this is distance from your house. So you're starting at your house. Okay? What's happening? You drive a little distance. At that point, you realize you forgot something at home. So you've been like accelerating to get up to this point. What should we do this in minutes? Should we make the graph reasonable, or should we make it non-reasonable graph? Like, so distance for kilometers. Okay, so at 1 minute you are 2 kilometers from home. I don't know how this is possible. We're making up stuff here. Okay. And then you realize you forgot something at home, so you head back home, and you get back home 2 minutes later. At this moment, you're now really late for school, so you go really fast on the way to school. Something happens here that you have to stop for a bit. This is where you're getting your ticket or something like that. And then you're more responsible and you finally get to school. So let's put some other values on here. This one right here is at 4,4. And then 6,6, and you got 5,5. What other points do I need on there? Okay. Oh, we need a point at 1. So at 1, we're at 1.5. So we're going to calculate what are the average rates of change between these values. Well, from 1 to 3, this is you were away from home and headed back home. So your average rate of change, the slope of that line, your change in y values went down 1.5. Your change in x values, you've went over 2. So we could say that the slope of that line from 1 to 3 is negative 0.75, and I guess this is kilometers per minute, according to the units that we made up, which is...
It's actually not that unreasonable. Like, if you just multiply it by 60, you're going
That's
around 90 kilometers an hour, which is pretty fast.
right. Well, maybe, yeah, on average, but we didn't, this little blip that we did in there is a little bit crazy. Okay? From 1 to 4, I'll draw that in a different color. We would be going from here to here if we wanted to find the average rate of change from 1 to 4. Well, now our slope, we have gone up from 1.5 to 4, so we've gone up 2.5 over 3 minutes. So it would be 2.5 divided by 3 kilometers per minute. And finally, from 4 to 5, you've just gone up 1 over 1. Choose a new color. So here, our average rate of is 1 kilometer per minute. Yes?
So why is it connecting to a point that isn't 1, 2, 1?
Well, it's, oh,
Slightly off.
yeah, I'm just slightly off, you're right. Because I originally drew 1,2 and then I relabeled it. We'll just pretend that this point is somewhere else. Okay. But the idea here is that is an average speed. How much you're going over that time, right? If you wanted to go a constant speed, that's what you would need to do from one time to another. If we were looking at our speedometer, what we'd be looking for, if I wanted to find out how fast was I going when I realized I was late for school, I would have to find the tangent at that point to figure out my instantaneous speed, what my actual speedometer was saying at that moment. So we noticed that to find the average rate of change is just finding the slope of a secant line between those 2 points. And that's the same as finding the slope of a line that we've done in the past, just your rise over run. Now, what we're going to do is apply our idea of a limit to find that instantaneous rate of change. So the idea looks like this. I've got some curve. And on that curve, I can connect 2 points, A and B. And with those 2 points, I could have a secant line. And the slope of that secant line would be my average rate of change from A to B. If I label everything on my diagram and I make a triangle, here's A to B. My horizontal distance is just whatever the x-coordinate of B is minus the x-coordinate of A. My vertical distance is whatever my y-coordinate of B is minus my y-coordinate of where A is. Does that make sense? And so with these labels, does it make sense that my slope from A to B is my rise, f of x minus f of A, just my change in y, divided by x minus A? What we want to do, and this is formula, the first formula we're going to look at. We have 2 different versions of this formula. What we're going to look at is saying, if I want to find this tangent line right here at A, if I want to find that tangent line at A, it's going to be the limit of this slope as x gets closer and closer to A. In other words, I'm going to imagine taking this point here and dragging it along the curve until I get closer and closer to that point there. This is the same diagram that we have. We have just the full circle drawn here. And the blue line is our secant line, and the red line is our tangent line. Right now, our blue line and our red line have different slopes. The idea of this limit is saying that if I make x, which is the coordinate here on this graph, it's at C, if I make that coordinate x get closer and closer to the coordinate of point B, then it should be that my secant line will get closer and closer to my tangent line. See how that works. As I drag C along the curve, you see how my secant line is getting closer and closer. And as I get closer and closer, and that triangle gets smaller and smaller, it's pretty accurate right now. But as you can see, it's not quite right. And if we put them exactly almost on top of each other, it works out almost perfectly. But the problem that occurs, if we go back to our notes, the problem that occurs is if I make x equal to a, I no longer have a triangle and I'm dividing by 0. So we have to be able to evaluate this limit in order to figure out what it is. So we're going to find the slope using that formula 1 of the equation of the tangent of this line at that point. So according to the formula that we had right there, our slope is going to equal the limit as x approaches, and we want to find it at the point 2. So as x gets closer to 2 of f of x, which is 3x squared minus 6x plus 1, minus f of 2, f of a, but a, we're getting close to 2. Can you see that this is equal just to 1? All over x minus 2. So right now we can't evaluate this limit because if I were to plug in 2, it would cause me to divide by 0. But if we simplify this, so this is the limit as x goes to 2 on the top. My equation is just 3x squared minus 6x. You might say you could factor out a 3x out of the top, leaving you with x minus 2. How convenient. Those x minus 2's will simplify. And at that point, once it simplifies, now we can evaluate the limit by just plugging in 2. And so we get a slope of 6. That means that our slope of our tangent at that point will be 6, or 6 over 1. Yes? Well, you'll always be able to use a technique, which so far this is nice, just factoring, worked out nicely. Sometimes you'll have to rationalize the numerator. Sometimes you're going to have to use your sum and difference of cubes to solve it. But that kind of idea. Now, there's some of you that have already taken some calculus, right? And you know how you could find the slope using our calculus techniques. But what we're doing right now is building up to that idea. Yes? You have to do it this way right now. Okay? Yes. Okay, try this one on your own. What's that? Or did the last one say find the equation of the tangent line? Yes, we didn't do that. Thank you. Okay, so now we've got the slope of our tangent line, and it also says to find the equation of the tangent line. Thank you. In order to do that, to find the equation of any line, you always need two pieces of information. You need a point and a slope. Doesn't necessarily have to be the x-intercept, but you need a point and a slope. So if I want to find the equation of the tangent line, I already know that the slope of my tangent line is 6. Do I know a point on my line?
2, 1.
Yes, it went through the point 2, 1, because it's that tangent at that point. So how do I find the equation from here? Well, there's two different formulas that you may remember from grade 10 that you might use. Some of you might decide, I want to use y equals mx plus b. So if you decide to use y equals mx plus b, what do we know? We know the slope is 6, and we know a point. That means when x is 2, y is 1. So I can plug in 2 for x, 1 for y, and the only thing I don't know is b. I can solve for b. Negative 11 equals b. So then I can write my equation of the line as y equals 6x minus 11. I find as you move further in grades, you tend to use y equals mx plus b more. For whatever reason, it comes to your memory quicker. Okay? There's also the point-slope form of a line. Okay, point-slope form of the line looks like this. If you have the point-slope form of a line, it has a place to plug in the slope, a place to plug in a point. So it just becomes y minus 1 equals 6x minus 2. If you distribute things, and like this will be 6x minus 12, add 1 to the other side, you get the same answer. Okay? Does anyone know where the point slope comes from? It's just your slope formula rearranged. Can you see that if you divided by this on this side, you just have your slope formula? And all you're doing in the point slope form is keeping one x and one y, and the other one you're putting in your point. So there's your connection for where these formulas come from if we're figuring them out. Nice. Okay, now you can try this one. All right, if you are ready to check how you did on this one, I will put up the answer there. We should have got a slope of 4. Okay, again, notation-wise, while we're working with the limit, we have to continue to write limit x approaches 1 until we can actually evaluate it. And we can't evaluate the limit while we're dividing by 0, but as soon as that x minus 1 simplifies, we'll get it equal to 4. Yes?
I make a variable for whatever's inside the limit function, call it something, and then say at the end that limit as x approaches 1 of that variable that I define equals 4. So I don't have to write that down every time.
No, you're going to have to write it down every time.
That'd be a pretty good snipe, just like
Yeah.
or something.
Can you just skip steps? Can you just write through?
Yes. So I wrote it out as if I was plugging in f of a here, because this time we're approaching the point 1, 3. But you have to remember that this point right here is technically a comma f of a, right? And so you can calculate this really quickly, that it's just going to be 3, and that's fine. And then once you get your slope, you've got your slope and your point. Again, I did it in both ways here. They come out to the same answer, whether you want to use the point slope form or the y equals mx plus b form. All good? Okay. So now, this is one way of looking at the secant to a tangent. The other way that we're going to look at it, same idea, but instead of having this as a point x and this as a point a and having the limit as x gets closer to a, we define this horizontal distance by some variable, in this case h. For those of you who have done Newton's quotient before, this is starting to look awfully familiar. Here's our point A, f of a. We've got a horizontal distance of h, so that means point B, the x-coordinate is going to be a plus h, and our y-coordinate is going to be f of a plus h. The slope of that secant line is still our vertical distance divided by a horizontal distance. And what we want to find, if we want to find our tangent, is now we want to find the limit as h goes to 0. There's a little typo in here. This should be an h on the bottom. So as h gets closer to 0, the slope of the secant becomes the slope of the tangent. Same idea as before. We want to take this diagram, we want to move point B along here so h gets smaller and smaller and smaller and smaller, and the limit as it gets closer and closer to 0 will be that slope of that tangent line. I think whatever it was here, it looks like it was a line got cut off. So this, you're right, this is a comma. It does look like a period, yes. Yeah, h is your horizontal distance, or your run if you were calculating slope. So now we can use this new formula to figure the tangent line. And you can examine some of the nice things and not nice things between the two formulas. The other formula, things canceled out really quite nicely, didn't they? So in this formula, what does this look like? Well, our slope is going to be the limit as h goes to 0 of f of 3 plus h. So what does that look like? Minus f of a all over h. So a little bit more I find in this one. A little bit more algebra to do. Again, we want to cancel out. So you might see that your numbers all simplify. You could factor out an h out of the top. Our h's simplify. And we get a slope of 6. Again, we can find our equation. We know that our slope is 6. It's going through the point 3, 5. B is equal to negative 13. So our equation of our line is y equals 6x minus 13. Yeah, I can go back up. So we plugged in a plus h, our point 3 plus h, so in this example, okay, what I'm going to do with this example is go back to the diagram. I'm going to pretend that this point here is the point where I want to find my tangent. It's at 3, 5. Okay? That means that this point up here, point B, its coordinates are going to be 3 plus h, because I've gone h to the right, and comma, whatever f of 3 plus h would be. Does that make sense? Whatever 3 plus h, if I plug that in, that's going to be the y coordinate there. Then my vertical distance is going to be this y coordinate, f of 3 plus h, minus this y coordinate, which is 5. In our example, f of 3 plus h, if I plug in 3 plus h in for x, I get 3 plus h all squared minus 4. The second value is just going to be minus 5, because that's that second value here. That will be my vertical distance. My horizontal distance is defined as h, so in our formula here, it's all divided by h. And now we just need to use our algebraic skills to expand things, combine like terms, factor, until we get that point where that h cancels out, because that's the whole thing holding our limit back. Once it does cancel out, we can solve for it, and we get our slope. Okay, try the next one, using the second formula. So this one, this idea of rationalizing the numerator comes back into play.
This one's fun too, though. One thing that I always, the one thing that I have to learn not to do is, I find that I would hear a variable at the bottom. I'm so used to automatically rationalizing the bottom, you then get right back to where you're at the top.
Yeah.
Like that habit you say where you do one thing, oh, factor, put back to factor form, oh, full factor, unfactor, defactor. Keep going right to the next thing. Remember when you showed us that? Where is that